So it's a different, this one we are going to think about whether we can sum to infinity.
No. I mean, you
You can sum to infinity. Let's have a look at what infinite geometric series is. All right? So now, with this, you should be able to define the concept of an infinite sum and review the ideas of convergence and divergence. Determine the geometric sum using a recursive process. Derive the infinite geometric sum or series formula and use it to calculate the infinite sum. Find the common ratio of first term given sufficient information and apply infinite geometric sums to applied problems involving exponential growth and decay. Now, in this case, do you think it applies to both exponential growth and decay or just decay itself?
So just say just decay.
Are you sure?
No, it's just exponential.
Okay, let's have a look. Let's have a look. Now, let's think about the geometric series. Yesterday, I talked to you about the sum of a geometric sequence is called geometric series. And I derive this formula for you to find the sum of n terms of the geometric series, where first term is a and the common ratio is r. Alright? So that's T1 and the common ratio is r. And for r less than 1, you can use this equation. If not r greater than 1, you can use this equation. Alright? And remember, r can never be equals to 1. Alright, next. So, if you look at the 4 graphs that I've plotted there, you can see when we have divergence and when we have convergence. Alright? Divergent means Tn will go to infinity or negative infinity. It occurs when r is greater than 1 or r is less than minus 1, or the absolute value of r is greater than 1. Convergent. It happens when r is between minus 1 and 1, which means the absolute value of r is less than 1. Alright? Think about it. Convergent, you are approaching one value. In this case, is 0. You're going closer and closer and closer to 0. Right? So think about the ball bouncing. Theoretically, it can go on and on and on and on and on and on. It doesn't stop. But there will be a point that it stops. Correct? Which means, can you sum to infinity? Yeah, because there will be some point that we can assume that it's 0 already. And therefore, you can sum the whole lot. Yeah? Whereas this one, that is not approaching any number, you cannot sum to infinity. Summing to infinity is still infinity. Whereas this one, you can think about getting really approaching 0 and assume that it's 0. Yes?
So we can just assume, because eventually it's just going to be adding like 0.000.
Yeah, that's correct.
More than it doesn't matter.
Absolutely right. Which means we can start deriving the equation for working out the infinity, working out the sum to infinity. Now, if we know that r is less than 1, as n approaches infinity, r to the power of n approaches 0, correct? If you do not believe me, you get a calculator out. Let's go 0.5 to the power of 1000. What does the calculator give you? Use your calculator and work out 0.5 to the power of 1000.
Small number.
Very, very small number.
0.
Yeah, could be. I actually don't know.
Well, you actually gave me 0.
Oh yeah, okay, fair enough.
Wow.
Thank you. So 0.5 to the power of 1000. Yeah, it is 9.33263,615 times 10 to the power of minus 302. Close enough to 0. Alright? Say if it is 10,000, it gives you 0. So you can see that as n approaches infinity, when r is less than 1, it's between 0 and 1, that will approach infinity, approach 0. Therefore, what happened? Sn equals 1 minus 0 at infinity, correct? Yeah? Yeah? So therefore, as infinity, as n approaches infinity, a equals 1 minus 0 divided by 1 minus r, and that is, that expression will give me 1, correct? So it's therefore a divided by 1 minus r. For r less than 1, the absolute value of r is less than 1. Can you write that down? I'm not sure whether this is in your formula sheet. Let me check. It is in the formula sheet. It is in the formula sheet. So, for r, absolute value of r less than 1, the sum to infinity is a divided by 1 minus r. That's all you need to know. And then we can start applying this. Alright, I'll move on. Happy for me to move on? Okay, not yet, that's fine. Alright, I'll move on. Now, by first identifying the common ratio between the terms, decide whether the following geometric sequence are convergent or divergent. If convergent, determine the sum to infinity. Alright, how do you determine if the sequence is divergent or convergent?
The ratio is less than 1.
Thank you. Or if it is greater than 1, it's not. Alright, try it.
B is a positive. B is convergent. Yeah. Or the other one. The wrong one. It's divergent. B is divergent because 11 over 10 is more than 1. And then A is convergent.
Yes, thank you. You're right. So you need to work out the r first. So if you can work out the r, you can work the sum to infinity. Eventually it will become 0. Agree?
Yeah.
So therefore, this is oops, go back. So therefore, you know that A is convergent and you can do the sum to infinity and it becomes 3. And then, whereas B, you cannot sum to infinity because it's divergent. It goes on and on and on and on. When we sum to infinity, it's just infinity in that case, and you can't really do that. All right, pretty straightforward question like this. Now, let's have a look at this question here. A geometric sequence is defined by this. All right, determine the rule for the nth term and hence state V5 as a fraction. Now, the rule. Question like this, determine the rule for the nth term. That means general rule. Alright, not explicit rule. You need to work out the explicit rule. And then you can work out what S5 is. Is this convergent or divergent?
It's divergent. Oh no, convergent. Because it's less.
Does it converge to one value? It's R is less than 1. So it is convergent, not divergent. So you should be able to work out the rule for the nth term, which is the general rule. Alright? And then you can work out V5. Again, I must stress that in the exam or test, be very careful with the terminology you use. You must always keep it, the notation, you must keep it consistent. If it is V, always use V and then V5. The notation must be very consistent. Do not use T. And now, Therefore, you should be able to work out S5. This one, because you know N is 5, you should be able to work out that in the sum. Alright? You can give it as a fraction, no problems at all. Since 28281 is not divisible by 9 anyway, so. Alright? So you can sum to infinity, which is 6561. A divided by 1 minus 8/9, which is 729 times 9. Alright? Happy with exercise 2? Exercise 3 is the typical ball problem. A ball is dropped from a height. We talked about it yesterday. Alright? It's the same same question, but you need to think about the total vertical distance traveled by a ball until the bounce stops. And think about H0 or H1. We discussed it yesterday. Yeah, we did. Exactly the same question yesterday, but I changed it slightly. Exactly the same question. No difference at all. See, I've drawn it again until it goes squiggly towards the end, it will stop. I mean, theoretically, it will not stop. Correct? Theoretically, you can still find a number. It's still smaller and smaller and smaller. However, yeah, you know R equals 16. You know what I've done? I've done something, I started A with 20. A should be 16. So I will change it in a few minutes. So, but, it doesn't really matter in this case. You know why? Because even if I assume that I started with 20, alright, I double it, I still take away the 20. So it should give you the same answer. It should give you the same answer.
So what do you mean?
So I started with 20. Ooh, I could. Yeah. All right. So you got to realize that whether you start with 16 or start with 20. I started with 20 and multiply by 2, therefore I take away 20. I take away, I double this, you see? I double this, that's why I take away that. Whereas if I start with 16, I just add that in, that's all. Yep. So it includes that twice. Alright, it includes the 20. Alright, so if you know, it's just 20, it's 16 divided by 0.2. So here I included the A. So you could actually, I use a different color. So if my fault for not working this correctly, if I use A equals to 16 meters, which is correct, which is a better, more correct in many ways. It's 16 over 1 minus 0.8, which is 80 meters. So therefore total distance equals to 2 times 180 plus 20. 2 times 80, not 180. 80 plus 20, which is 180 meters as well. Same way. It's just different way of thinking, that's all. Alright? Now, let's go to the next slide. It's a quick summary of sequences and series. This one, a first order linear recurrence relation. We don't really do it in year 11 methods, but if you're moving on to year 12 application, this is quite important. We will, if you move on to the year 12 applications, we do a lot of first order linear recurrence relation, which means if you take the R away, it becomes a arithmetic sequence, correct?
Yes.
If I take the D away, it becomes a geometric sequence. Alright? So, first order linear recurrence relation is a combination of both. So Tn plus 1 equals to R times Tn plus D. And T1 equals to A. So the two important generalization. A first order linear recurrence relation becomes an arithmetic sequence if R equals to 1. Alright, it cannot be another value. A first order linear recurrence relation becomes a geometric sequence if D equals to 0. Alright? So you need to think about the R and the D in this case. So it's just a quick summary. You can combine both the arithmetic and geometric, and it will become a first order linear recurrence relation. Alright, next one, the last slide I would say. The nature of the long-term behavior and recurrence relation. It can become obvious in the list, table or graph that the type of recurrence relation we are dealing with and the nature of the long-term states in the sequence. There are three main types of long-term states. Long-term increasing state, as in when n approaches infinity, Tn approaches infinity as well. So decreasing state, when n approaches infinity, Tn approaches minus infinity. Alright? So long-term steady state, if a recurrence relation has a long-term steady state, then over a long period of time, the sequence will tend to a particular value. So, 0 if it is geometric sequence, whereas if it is first order linear, there is a particular value. Alright? Because of the plus D. Alright, there's a particular value you can look at. Could be up and down. So in this case, if n approaches infinity, Tn approaches a particular value. Alright? I'll just put it in a bracket here like this, a box here like this. So generally when we are looking at geometric sequence, Tn will approach 0. Alright? So that's all I have for you today. What I'm going to do is I'll give you some time to do some work today, and tomorrow you will have some time to do some homework catch up as well. Alright?